Okay, good morning, everyone. Any questions? Please put your question on chat while the rest of the class join in. Okay. Okay, so yesterday we introduced the notion of the Taylor polynomial, which is a way to approximate a function locally by a polynomial. And so let us remember the formula for Taylor polynomial of degree n. We have to remember the format. So it's f at the point A. So here we're doing the approximation at the point A or near it, plus f prime of A, x minus A, plus f double prime of A, the second derivative, x minus A square, plus we keep going up to the nth order. So which gonna give me the nth derivative at A over n factorial x minus a to the power n. And the idea that near x equal to a, the function f can be approximated by its Taylor polynomial. The higher the order, the better the approximation. That's really the idea. So let's look at number 10 and 28. So number 10. So we have the following function, f of x equal 1 over x squared. And the question is, find the linear approximation at the given point, find the quadratic approximation at the given point, and then use the approximation to estimate 1.05. So they want us to find the linear. Linear, it means basically find the tangent line and use the tangent line to approximate. Then they want us to find the quadratic. The quadratic, it means up to degree 2. So that's the quadratic one. And we want to find the approximation near a equal to 1. All right, so we'll do that easily. So to find the linear or the quadratic, I need the first derivative and the second derivative. So f of x equal, because I need derivative, I'm going to rewrite it x to the minus 2, which is going to give me at 1, we have 1. This first derivative is minus 2, x to the power minus 2 minus 1. It means the first derivative is minus 2. And we only need the second because they only want the quadratic. Is equal minus minus plus, so it's 6, x to the minus 4. But we're interested in the derivative at 1, which is equal to 6. So the linear approximation becomes, so the linear. So the linear approximation means basically the tangent line. So that's, we're going to call it P1. So that's the degree, point of degree 1. It's f of a, f of 1. My base point is 1 plus the derivative at 1 times x minus a, which is 1. So P1 of x equal 1 plus x minus 1. Okay, now I know that this is x, but that's really the first degree Taylor polynomial. So that's the linear approximation. Now the quadratic. Quadratic, it means I want the P2, which is f of 1 plus f prime of 1 times x minus 1 plus the second derivative. The second derivative is, no wait, I did a stupid mistake, didn't I? Nobody corrected me. Are you guys awake? I did a stupid mistake. F prime at 1 is minus 2. So that's the first one. So plus the second derivative is 6. divided by 2 factorial x minus 1 squared. It means the second degree, the quadratic approximation is 1 minus 2 times x minus 1 plus 2 factorial is 2, 6 over 2, it's a 3, x minus 1 squared. Okay. So, and the picture is that this is the function, the graph of the function. 1 over x squared looks like that. So that's the original function. That's the base point. Near this point, we're doing the approximation. P1 is the tangent line. That's P1, should look like that. That's the P1, that's the tangent line. And P2 is a parabola like, which is gonna be closer to the function than the tangent line. So it's gonna hug the function a little bit more. This is gonna be P2. And this one is the function. This is f of x equal 1 over x squared. So that's really the picture. And the approximation is near the point 1. It means as we move farther away from 1, very far away from 1, of course, the whole approximation is falling apart. Now they want me to use the approximation to estimate So, okay, so I want to estimate 1 over 1.05 square. Okay, we're going to estimate this. So let's see how the estimate would work. Okay, what we have is, so we're going to use linear first. The idea is that the function is close to, it is first to P1 of x. That's P1 of x. But it's closer to P2. But now we're going to use P1 to approximate it. So we need f at 1.05. That's the 1.05 square. So this is approximated by this at 1.05. Which is equal to 1 minus 2 times 1.05 minus 1. It means 1 minus 2 times 0.05. And now it's just a matter of evaluating. So this is 1 minus 0.1, which is 0.9. Okay, so that's the linear approximation. Now we're going to use the quadratic. Again, it's the same idea. So here my function is near x equal to 1. The function is almost equal to the second degree Taylor polynomial. So f at 1.05, which is 1 over. We're going to approximate it with the polynomial at 1.05. It means I plug in 1.05 in the expression of the polynomial, as simple as that. So this will give me the following. 1 minus 2 times. I'm plugging 1.05 for x in the polynomial. Plus 3 times, again, I'm plugging x in the expression square. And the rest is we pick up a calculator and see how well we're doing. So that's 0.05 plus 3 times 0.05 square. So 1 over is being approximated by that. So now this is equal to all right, now we just pick up a calculator and see what we got. So we're going to have 1 minus 2 times 0.05 plus 3 times 0.05 squared. So I'm getting 0.9075. Okay, that's the approximation. Now let us compare to the actual value. So let's see the actual value is, it means I evaluate exactly this expression and see how well is my approximation using the polynomial. So I do that. I'm getting 0.90729 basically. So that's the actual value. It means that we have the approximation is not bad, even we're using only the second degree. This is, they agree on the first 3 decimal and they start disagreeing after that. It means the absolute error is of the order of 10 to the minus 3. Okay, question before I move on. Okay, so we're going to look at number 28 and then we move on. Number 28. So f of x equal the square root of x. And a equal to 9. And the question is, find the nth degree Taylor polynomial for n equal to 1 and 2, and then graph it. So it's basically the same thing. Chris, are those the questions you're having?
Yes.
Okay, so what actually bothered you in this problem?
I think it was the second degree and the graphing that got me. I don't know why. For some reason, I could do the first graph, but I just could not do the second degree.
Okay. Basically, you don't have to do it exactly. Basically, the idea is to understand how it looks. Okay, so let me see. So let us do it very quickly. F of x is the square root of x. It means f of 9 is the square root of 9, which is 3. Now f prime. And to be able to find f, I need this to x to the power a half. So this is x to the power a half minus 1. It means f prime at 9 is 1 over the 2 square root of 9 is 1 over 6. Please, if I do any stupid mistake, let me know. Now, the second derivative, it's minus 1 over 4, x to the minus 3 half. It means the second derivative at 9 is minus 1 over 4 times 9 to the power 3 half. Now 9 to the power 3 half is 3 to the power 3. It means 4 times 27, which is minus 1 over, that's in 8, minus 108, unless I did a stupid mistake. So the linear become P1 of x is f of 3 plus, sorry, f of the 3 plus the derivative x minus 3. And the quadratic become P2 of x equal 3 plus, so the first 2 terms are the same. And then we add the second derivative, so plus. The second derivative is minus 1 over 108 divided by 2 factorial times x minus 3 to the power 2. So that's the second degree polynomial. One over, that's going to give me 6 to 116 x minus 3 squared. All right. Now, what about the graphing? The graphing part is the following. First, we graph the function. So that's the square root of x function. That's really my graph. And we take the point 9. That's my base point. All right, P1, of course, you know it. It's nothing more than the tangent line. So this is P1. That's P1. P2, the idea behind the graph in it is the following. Sorry. Well, my mind is scattered today. That's 9. 9, and 9. You guys should correct me if I do something wrong. All right. P2, the only thing we should know about it is that at 9, it means if I plug in 9 in here, I will get exactly 3. This is the point 3. So the value at 9 is the same as the value of the function. The second property it has, if I find the derivative of the second polynomial at 9, I will get exactly the derivative of the original function at 9, which is 1 over 6. So the derivative of p, let's see what I'm talking about. If I take p derivative of this and I evaluate it at 9, that's really the idea, I get exactly the value of the derivative of the function at 9. It means 1 over 6. So the parabola will have this as tangent line. It will have this as, it go through this point. It have the same derivative as the function. The other property it will have is that if we take it, find its second derivative, it will be the exact thing as the derivative of the original function at 9. It means it will have the same concavity. So basically you have a parabola. That's the tangent line to the parabola and the same concavity at the function. So the only thing you want to know is that it's going to look something like that. Something like this. It have the same concavity. We don't have to graph it exactly. It will have the same concavity. It means it cannot look like this. It can't look like that. It will have the same tangent line and the same concavity. So even though it's a parabola, it's not going to be, in this particular case, a parabola going up. It's going to have to be a parabola going down. Okay, that's about what you have to figure out about the sketching. Right. Okay, any other questions? So let's see what we have so far. What we have is that, and how we are going to move a little bit. So we're moving to section 11.2, notion of power series. But let's see what's the motivation of the idea of power series. Okay, the motivation is the following. Let us say I take a simple function, f of x equal e to the x. Very, very simple function. Right? Pretend to be simple. And at a equal to 0, I'm going to find its Taylor polynomials. All right, so f x equal e to the x at a equal to 0. Let us say I want to find its Taylor polynomial of degree 5. So if I want to find it of degree 5, remember I need up to the 5th derivative. So e to the x, it means at 0, it's 1. I plug in here. F prime is e to the x. It means f prime at 0 is 1. All right, so I took in a simple function on purpose. F double prime is e to the x. Double prime at 0 is 1. So all the derivatives of any order for the f of x equal e to the x is 1. So if I want the 5th order Taylor derivative, Taylor polynomial, so we're going to get f of 0, it's 1, plus f prime at 0 times x, plus the second derivative at 0 over 2 factorial x squared, plus the third derivative, x5, sorry, x3, plus x4, plus. So it's just really a polynomial. Okay, so that's the 5th order Taylor polynomial. The 6th order, you're going to add 1 over 6 factorial x6. All right. Now, the idea behind those, as I said, is that near x equals 0, e to the x can be approximated by those polynomials. So I can approximate it by the first two, the linear. If I need a better one, I go quadratic. If I need a better, I go cubic. If I need better, the 4th degree, better the 5th degree, and so on and so forth. So the idea is, here is the following. This is a polynomial. And the idea that if I take more and more term, I get a better and better approximation. So this is going to motivate the notion of the idea of a polynomial, if you want, of infinite degree. Means the more terms I take, the better approximation. So the question is, why don't we keep going and taking more and more terms? And this is going to basically motivate the notion of a polynomial of infinite degree. That's what we're going to call power series. It means the idea of keep adding and adding and adding, never stopping. Because the higher the degree, the better the approximation. The question, so why don't you keep going and take a series where these are the polynomials are the partial sums of those series. So what is a power series? Power series is basically the general definition. It's a generalized idea of a polynomial. So it's a polynomial, if you want, quote unquote, with infinite degree. So now let's define it in a very formal way. So a power series. A power series in x minus a, because as you realize, sometimes if I want an approximation near a, I have to use Taylor polynomial in x minus a. A power series in x minus a is a series of the form of the following form. C0 plus a certain coefficient. C1 x minus a. So it's a polynomial without really stopping. C2 x minus a squared plus C3 x minus a to the power 3 plus etc., etc., etc. So a power series in x minus a is a series of this form. So in sigma notation, it's a series of the form sigma c sub n x minus a to the power n equal 0 to infinity. Now, if I take a equal to 0, so when I take a Taylor polynomial where the center is at 0, if a equal to 0, the power series will have the 4, because those come up a lot actually, has the 4, the following form, sigma, it will become Cn xn, n equal 0 to infinity. So a power series in x will have this form. And so on. Okay, so it's a generalized form of a polynomial. It's a polynomial, if you want to think about it, of infinite degree. And what motivates the idea is Taylor polynomial. Since the higher the degree, the better approximation. So the idea was, okay, why don't we just take a series where the partial sums are polynomial? That's really where the idea is coming from. Now let us note here. In a power series, C0, C1, C2, C3, etc., are called coefficients of the power series. Okay, x is a variable. X is a variable, so x is going to change. All right, so now here is the question we're gonna address. Example of a power series. A typical example of a power series is something like that. Let me take this power series. 1 plus x squared plus x cubed plus x4 plus so on and so forth. So this is a simple power series. It means sigma xn, n equals 0 to infinity. Okay. Now, x here is a variable. So the constant here, C0 is 1 in this simple series. C1 is 1, C2 is 1, C3 is 1, and so on and so forth. So this is a power series. X changes. Now, as x changes, the series may converge for some x, may converge for some values of x, and diverge for other values. Because x is a variable. So there are some values of x I can plug in here and I get convergence, and some values of x I plug in here and the series diverge. So I'm going to ask you now a very a very simple question. Who can give me a value of x for which the series converge? So my question is, question number 1 concerning the same series. Does the series converge? Does the series, this power series, converge for x equal a half? What does this mean? What does this mean? Means that if I plug in a half in here, will the series converge? Yes or no? So a power series is going to be a series that involve a variable x. And then for some x's, this series will converge. It means actually I have an answer here. For some, it won't. So if I take this example, I tell you, does the series converge for x equal a half? What does this mean? It means that if I plug 1/2 into this expression, will the series converge? So it means if we plug 1/2, 1/2 for x in the expression of the series, in the series, does it converge? Does it converge? That's really my question. So let's do that. Let's plug in 1/2. I will get 1 plus a half plus a half square plus so on. Does the series converge? Yes or no? What do you think? Yes,
because of the geometric series.
Absolutely. Does it converge? The answer is yes, because it's a geometric. So that's why I gave you a geometric series with ratio. So geometric series with ratio equal 1/2. R is less than 1. Series converge. So does the power series, I should here write power, series converge for x equal a half is basically a question. If you plug in a half into it, will we have an answer? Now, B, a simple question. Who can give me a value of x for which this power series does not converge? Who can give to that's the power series? Give me a value of x that said the series does not converge. Means when I plug x in the expression, actually it's gonna blow up. X equal to 2. So if I take x equal to 2, the series absolutely the power series diverges. Because I will be taking 1 plus 2 squared plus 2 cubed plus 2 to the power 4 and so on and so forth. Okay, so a power series is basically a series that depends on a variable x. It may converge for some and it diverges for others. So the question addressed, so this problem I gave, as I said, it's a simple problem because we know geometry. So here, if I plug in 1/2, it's going to converge. 1/3, it will converge. It will converge as long as absolute x is less than 1. It's going to diverge otherwise. So the problem is, now the question is, if I have a series which is not as simple as that, how can I determine for which axis does the series converge and for which axis does the power series diverge? Okay, so we're going to consider the following problem. Let's consider the power series, the following power series. Okay. So the question in general is the following. How to find? How to find the values of x when the power series converge? series converges. That's really will be our main concern. All right, before I take problems and do this question, which is not very hard, I have to remind you of something. Let us recall a few facts about absolute values. Right. Suppose I tell you the following. Solve absolute value of x less than 3. What do I mean by that? It means find all the x's that satisfies the absolute x less than 3. How do I solve this? Solve absolute x less than 3. It means where is x? What is x? If an absolute value is less than 3, it means the values of x should hover between what and what? Back to you.
Negative infinity and 3.
No. Because this is what? Absolute value. So can the absolute value can x take -4?
No, it could be between -3 and +3.
It has to be between -3 and +3. Absolutely. Yeah. Okay, because an absolute value is less than 3, it cannot be -4. It cannot be -3.1. So the smallest value it could be is -3. So if an absolute value is less than 3, it means x has to be between 3 and -3. So graphically, if this is 0, if the absolute value is less than 3, it means that's my x. My x has to be between -3 and 3. It means distance to 0 is less than 3. So in general, suppose r is a constant. R is a number. Suppose r is a constant. Then, if the absolute value of x is less than 3, it means that x has to be between r, that's the largest value it can take, and -r is the smallest it can take. It cannot take anything else. Okay, so that's what it means, absolute value. All right, now we need 2 ideas about the absolute value. I start with this one, and then later on I will take another idea. But that's very important. That's what means the absolute value, because I cannot take -4. It cannot be -3.1. The smallest has to be -3. Otherwise, the absolute value will not be less than 3. So now I'm going to consider the following problem. Problem is, okay. This is done right here. Let's consider the series. The following series. Sigma n equals 0 to infinity of x to the n over, let us say, n squared times 2 to the n. Okay, that's a typical power series. So if we write up a little bit the term, actually I cannot start at 1. If I write up the little bit of term, I will get the first term is x over 2 plus the second term. Actually, I like to write it like this, x squared times. So the second term is going to be 1 over, if n is 2, so I'm going to have 2 squared times 2 squared plus. So that's really how it looks like. If n is 3, I will have 3 squared, 2 cubed, and so on and so forth. So in terms of constant, what's the C0 here? What's the C1? What's the C2? And what's the C3? And there is dot, dot, dot. We didn't finish. C0 is usually the constant term in the expression of my power series. Here, there is no constant term. So C0 for us is going to be equal to 0. What is C1? C1 is the coefficient of x. It means what x is multiplied by. So what's C1 in this scenario? It means what is x multiplied by?
2.
No.
1/16.
Where are you getting 1/16 from? Coefficient of x. If this is x over 2, x is multiplied by what? By half. All right? C1 is the coefficient of x. C2 is the coefficient of x squared. So what's the coefficient of x squared? It means what is x squared multiplied by? Quickly.
1/16.
That's 1/16. What's C3? It means what's x3 multiplied by? This is x3. What's x3 multiplied by? That's what we call by C3. That's what we call the coefficient of the series. So this is going to be 1 over, that's a 9. So basically 3 squared times 2 to the power 3, okay, which is 1 over 72. So that's what we mean by C0, C1, C2. So C0 is the constant term in this power series. C1 is what x multiplied by, which is a half. C2 is what x squared. C3 is what x cubed, and so on and so forth. So this is
I
just
have a question.
Yes, please.
Where'd you get C0 from? I mean, where'd you get the 0 from?
Okay, in the picture of a series, a general format of a series, C0 is usually the constant term, the one that doesn't come with an x in it. Chris, are you with me?
Yeah. What do you mean by that?
What? So if I take what? If I take a polynomial, suppose the way you guys wrote a simple polynomial, 1 plus x plus 2x squared, all right? And I say that a general polynomial look like this. That's the form of a general polynomial of degree 2, okay? So let us agree on this notation. A general polynomial of degree 2 has this form. Do you agree with me on that?
Yes.
Okay, so if I take this as an example, what played the role of C0 in this problem?
Would it be the 1?
Right. What's played the role of C1?
X.
Right. But no. C1 will be what x is multiplied by.
Oh, so it'd be 1.
Exactly. What's C2?
2.
Okay. Now suppose I take another polynomial. 1 minus a, so 4 minus x plus a half x squared. Okay. In this polynomial, what's C0? Quickly.
Would it be 4?
It will be 4. The constant term, the term that doesn't come with x next to it. It's the value at 0, basically. What's C1?
-1.
Right. What's C2?
1/2.
1/2, exactly. So one more question. Suppose I give you 2x minus 3x squared. That's polynomial of degree 2. What's the C0 here? What's the constant term?
Oh, it'd be 0 because there's nothing
Right.
there.
Exactly. It would be 0. What's C1?
2.
And what's C2?
-3.
Is
I mean,
making-
yeah. Yeah, okay. Yeah, okay. That makes a lot more sense now.
Oh, thank you. All right. So that's really what's happening here. That's exactly the same format. You think of a power series as a generalized polynomial. That's really how we think of a power series. All right. Now the question is the following. I'm reading the copy. Question is, for what values of x does the series converge? Sometimes we call this find the interval of convergence. So for what value of x? It means which axis I can plug in here and it gives me convergence. So for what values of x does the series converge? Or another way of asking the question is find the interval of convergence. Okay, how are we going to solve this type of problem? Okay, looks complicated, and the question is which values will allow convergence? Who can give me one value where the series is convergent? Can anybody give me one value? Easiest possible value under the sun. What do you
1.
think?
1.
What?
Yeah, 1.
1, I don't know why though. You have to think about it, 1. I want one that you don't have to think about. 1, it means you have to convince me that the series 1/2 plus 1 over this plus 1 over that converge. I want a number that you don't have to think about.
0.
Right, 0. The series will converge for 0. I'm not even thinking anymore. Just plug in 0 in here. 0 plus 0 plus 0. That's the honest to goodness 0. The series converge. That's a number that we don't really have to think about. 1, I have to think about it, but I don't want that. We're going to figure them out all. So now the question, for what values does the series converge? And the way we're going to do those problems, we're going to use the ratio test. We will use the ratio test. And you will see how we are going to use the ratio test. We use it as follows. Let's see what does the ratio test tells me. First, what is the general term? Okay, I used an instead of k. I forgot what the book is using here. So an is the general term. So the general term is x to the n over n squared 2 to the n. Okay. The ratio test requires us to take the ratio between an plus 1 and an. So let's see what's an plus 1. Is x to the n plus 1 over n plus 1 squared 2 to the n plus 1. Okay. The ratio test tells me that you have to compute the ratio. So we're going to compute the ratio. So let R be the limit as n tends to infinity of. Remember, the ratio test requires the absolute value. An plus 1 over an. Okay, this is equal to the limit as n tends to infinity of the absolute value here. So this will become x to the n plus 1 over n plus 1 squared 2 to the n plus 1 over the absolute value xn over n squared 2 to the n. And now I'm going to use a lot of the property of the absolute value, which tells me the following. And for the absolute value, if you have the absolute value of a over b, okay, those are properties that we can prove. It's the absolute value of a over the absolute value of b. So we can break the absolute value this way. So how I'm going to use this? So it's going to be equal. The absolute value of x to the n plus 1 over the absolute value of the denominator over absolute value of x to the n. The absolute value is important, our problem now, over 2 to the n. Okay. Now, which terms I should keep the absolute values and which term I need to throw them away? I don't need them. Watch carefully. The denominator is positive. So absolute value in the denominator is useless because that's a positive term. So this is n squared 2 to the n. What about the numerator? Do we need the absolute value? What do you think? Can x be a negative number? Let me put it this way. X is a variable. X could be positive and x could be negative as well. So I cannot basically remove, because the question is for which axis does it converge? So since x is a variable, it could be negative or it could be positive. So I cannot remove the absolute value from this x because x could be negative. The only thing I know for absolute value that the absolute value of x to the n plus 1 is equal to the absolute x to the n plus 1. That's the only thing I know. But I have to keep the absolute value because x could take negative value. So now I'm going to have x to the n plus 1. So it looks a little bit messy, but we're almost done with the mess. And so this is the limit, and this is the limit. So finally, this is equal to the limit as n tends to infinity of absolute value. So we're going to flip things around. N plus 1 over n plus 1 squared times 2 to the n plus 1. So something we did, multiplied by n squared 2 to the n over absolute x to the n. Now the ratio test, when we did the ratio test, remember we kind of put the like terms together so we can really work with it. I'm going to do verbatim the same thing. So then this is going to be equal to. So R from the ratio is the limit as n tends to infinity of the like term together to be able to find the limit. I will have 2 to the n over 2 to the n plus 1 times absolute value of x plus n, x to the power n over that. And now finally, let's compute the limit of that, equal to. Now, the limit as n tends to infinity of n squared over n plus 1 squared. The easy way to do it is take n over n plus 1. 2 to the n over 2 to the n plus 1, as you remember, is 2 to the n times 2. Finally, absolute x to the n plus 1 over absolute x, again, is absolute value to the x times x over that. So exactly the way we did the ratio test. So finally, I will get this term will go to 1. 2 to the n, simplify. X to the n, simplify. I will be left with absolute value of x over 2. So the ratio test gave me that so far. Now, what does the ratio test tell me? The ratio test tells me that if this ratio is less than 1, the series converge. If it's bigger than 1, the series diverge. Equal to 1 is inconclusive. So now we're going to do the discussion. And our discussion is going to depend on the ratio test. So by the ratio test, what do we have? By the ratio test. Okay. We have the series converges for when absolute x over 2 is less than 1. Okay, so by the ratio test, the series converge when absolute x over 2 is less than 1. What does this mean? It means when the absolute value of x is less than 2. But when is the absolute value of x less than 2? It means when x is between -2 and 2. So now I'm going to start drawing the number line. This is my 0. This is -2. And this is 2. And the ratio test tells me if I pick anything between those two, if I pick any value between -2 and 2, my series will actually converge. Means if I plug in 0 in it, 1 in it, no, 1.5 in it, I will have a convergent series. Now, the series diverges. About the ratio test, when absolute x over 2 is strictly bigger than 1. So now we have here convergence. Converge. Up here, it diverges. If I take anything, that's why it's called the interval of convergence. So series diverge when absolute x over 2 bigger than 1. It means when x is larger than 2 or x less than -2. Then the series will diverge. Okay. Now, we still have the endpoint. Okay. Now, the ratio test, if you remember, the ratio test is inconclusive when the ratio is equal to 1. So the ratio test tells me as long as you are between -2 and 2, it converges. -2 not included, 2 not included. Outside this, it diverges. When this is equal to 1, the ratio test gives me no result. It means if I plug in 2 in the series and I use the ratio test, I'm going to get 1. So now how are we going to handle the ratio test? Okay. So the ratio test is inconclusive when this. It means when x equal to 2 and x equal -2. Right, so we're going to those to be treated separately. So we treat those 2 points separately. Because the ratio test doesn't give me a result. So what do I mean by treat them separately? Right. We do it like this. For x equal to 2, we're going to plug x equal to 2 in the expression of the power series. Let's see what do we get. It means we take our original power series, which is x to the n over n squared 2 to the n from 1 to infinity. And I plug in 2 for x. So this x, I put 2. I will have 2 to the n over n squared over 2 to the n. So I just plug in 2 for it. Now, if I do that, those 2 to the n simplify, I will have 1 over n squared. Now, does this series converge or not? So the ratio test, when x equal to 2, is going to bring up a situation where the ratio test cannot be applied. So if x equal to 2, the series will have this value, which is converges, because it becomes a p series, p equal to 2. It means if I go back to my interval, everything between -2 and 2 converge, and it's going to also converge at 2. It means if I plug in 2 into the power series, the series will converge. Now, finally, what happened at the other end point? X equal -2. So I want to know what's happening at -2. I plug in -2 into the power series. I will have sigma x to the n over n squared 2 to the n. I'm going to put -2 to the n here. So this is -2 to the n over n squared 2 to the n. Now this look a little bit complicated, but is it complicated? Let us note something simple. I will note something simple and then we will be done, because -2 to the n is equal to what? How can I rewrite this so that I can kind of simplify the math here? -2 to the n, I can rewrite it as -1 to the n times 2 to the n. I can basically rewrite it this way, and that's really crucial. Okay, so -2 to the n is -1 to the n times 2 to the n. That's why those are exactly the same thing. If n is equal to 0, 1 and 1. If n is 1, of course, that's negative 2. If n is 2, I will have 4, and I will have 4. If n is 3, -8, -8. And what's the benefit of doing this? Over n squared 2 to the n. Okay, now those two will cancel each other out, and this will give me sigma -1 to the n over n squared. Now this one converge as well, because by the alternating series test. 1 over n squared goes to 0, and it is really a decreasing sequence. So it means that the power series will converge for x between -2 and 2. -2 and 2 are included. So the interval of convergence is the closed interval -2 and 2. Means if I take any value of x in here, plug it into the expression of the series, I will have conversion. So there are a lot of values. Anything outside that, I plug it in here, I will have divergence. Okay, so that's it for today. The book does this problem in 2 ways. They use the ratio test, and they use another test called the root test. Do not be concerned with the root test at all. Okay, the way I want you to do those problems is exactly the way I am doing them. I did them on the board right now using the ratio test. And of course, tomorrow I will do a lot more to practice. Right, the class is dismissed. If anybody has questions, as usual.